So the next type of application we want to look at involving radian measure has to do with linear and angular speeds. Now, when we think about linear speed, we've got speed here. So let's look at linear speed. So when we think about linear speed, we're going to define linear speed, which we can think of as velocity, as the change in the arc length over time, right? We've already defined arc length as s over t. Now, what does that look like geometrically? When we think about linear speed, what we're talking about is if I have a point here on the outside of the circle, I want to know how fast is that point changing, right? How far is that distance changing relative to time? So at what speed is it changing, right? A P moves at a constant speed along the circle. So it has to do with the length or the distance it's traveling over time, which is what we think of for velocity anyway. So linear speed has to do with how fast this distance along the outside of a circle, let's say, is changing in respect to time. Compare that to angular speed here, which is defined as omega, which kind of looks like a W. And that has to do with how fast the angle is changing with respect to time. So how fast is theta changing with respect to time? So although we have this point P, which is traveling around in a circle, what we're interested in is how fast is this angle representing where P is at, right? How fast is the angle changing with respect to time? Now, one thing to note over here is we already discussed that we defined radian measure, right? We defined an arc length as S is equal to R theta, okay? We can also say, well, linear speed, which is defined as S over T, well, if we want to think about arc length as R theta, right? R theta now over T, because anytime we're thinking about these speeds, linear or angular, it has to be with respect to time. So what we have here then is an alternate way for us to be able to represent the angular speed, or the linear speed, excuse me. We have an alternate way of being able to represent linear speed, v, velocity, which can also be represented as the radius times omega. It's really just a derivation, or a substitution, I should say, not derivation, but a substitution using the original idea of arc length, substituting in for theta over time, and we end up with r times omega, which is theta over time. So sometimes it's easier to use that notation. Well, let's look at an example here that we might come in contact with. And this happens to say we have wind turbines. Now, hopefully all of us are pretty familiar with these wind turbines. We see them a lot now out in the countryside or even along the side of the highways. So we have the blades of a wind turbine, which are 116 feet long. And we know that the propeller is going to rotate at 15 revolutions per minute. We want to find the angular speed of the propeller in radians per minute. And we also want to find the linear speed at the tip of the blade. So having read through this the first time, we need to kind of come in here and look at a couple of things. We know that the blade, right, the blade of the turbine is 116 feet long. Okay, so let's draw a picture really fast. If I have this turbine, this wind turbine, and I have the center here, and we know that we have these blades that are typically, I think there's only 3 blades, but I'm going to put 4 in here. We know that these blades are going to rotate around in my somewhat of a circle here. We also know that the length of that blade is 116 feet long. So that right there becomes the radius. Now the next thing we need to know is we are given in the problem that the propeller rotates at 15 revolutions per minute. Now that's important to us. We know that one revolution would be equal to 2 pi. So if we're thinking in terms of rotation, we're talking about theta here. So theta says that we're going to rotate 15 revolutions. But we have to change this into per minute, but we have to change this into radians. Remember that when we're dealing with these radian applications, every time we think of theta, it has to be in terms of radians. So if I'm going to change this into radians, if I know that one revolution is 2 pi, then I'm going to multiply 15 revolutions by 2 pi, and I end up with 15 times 2, which would be 30 pi radians. So I took it out of revolutions per minute and put it into radians. Okay, so that's how we're converting this. So now I know that the radius is 116 feet. I know that the angle I'm interested in is 30 pi radians. And I can move on and I can now answer the two questions. So I want to find the angular speed. The angular speed, which we defined earlier as omega or W, it's equal to theta over time. Now we have said that theta was 30 pi radians per minute, per 1 minute. So there you go. That's our angular speed, 30 pi radians per minute. And that's that's the exact measure, in other words. The decimal measure would be if you multiplied 30 times pi, and then you would have the decimal value. Now, the linear speed, but we did answer it anyway in radians per minute. The linear speed that we're looking for says linear speed has to do with the velocity. Now we've said that velocity was equal to arc length over time. We also defined this as arc length we know is r theta over time, or in other words, theta over time would just be r times w, right? We went through that whole substitution. Well, if that's the case, then I know r was defined as 116 feet. I'm going to multiply that by omega, which we said was 30 pi radians per 1 minute. And when I do multiply these things, so I'm going to multiply 116 by 30, and when I do multiply those things together, I find out that this is 10,933 feet per minute, is how fast the tip of that blade is rotating. So this is kind of an example of using those formulas for both linear and angular speed, and you can see how we would walk through the steps. Don't forget that anytime you're dealing with theta in these radian formulas, you have to have theta in terms of radians. That's where most students make their mistakes.